In today's lesson, we're going to be discussing some of the properties of planes, and then we're going to look at some of the possibilities for the intersection of lines and planes. First, we're going to look at the scalar equation for a plane, where again, the coefficients of x, y, and z represent our normal. I just have this little note for you in blue here. Any vector parallel to the normal is also normal to the plane. So any scalar multiples that you have will also be normal to that plane. And then in green, you'll see here, any points on the plane will satisfy the scalar equation. So if you were to do a left side, right side check, that would be equal. And then the last point in yellow here, a normal and a point can be used to define a plane. So instead of the two vectors that we normally use to define the plane with a point, if we know the normal and a point, we can use that. So before moving on, I just wanted to quickly refresh your minds. So in two space, there are three possibilities when considering how two lines will intersect. So case number one here, I have line 1 and line 2, and they're intersecting at one single point. So in this case, we would have one solution. Case number 2, we have two lines that are parallel but different. So in this case, we would have no solutions. And then case number 3, we have two lines that are identical. And in this case, we would have an infinite amount of solutions. So they're intersecting everywhere. When we're dealing with lines in 3 space, there are 4 possible intersections. So the first case number 1, top left here, we have one solution. So just like on the last slide, the two lines meet at one point. Second case, we will just go down. So this is the case where the two lines are parallel and there's no solution. Third case, top right, this is the case where the two lines are the exact same. They're coinciding, we can call them. We can say that these two lines are coincident, and there's an infinite amount of solutions. And the fourth case, the bottom right, this is a really strange one. So there's no solutions in this case. I'll just write that in here. But it's a little bit harder to see. So I'm just going to kind of explain what I did to this diagram. So the blue line, line 1, our green line is line 2. I just erased part of the line because I wanted to show that this line is underneath of line 1, but doesn't touch it at all. So if you imagine this 3 space and you have two lines that just never cross, but they're not parallel. That's what this case is. And we can call these skew lines. We're going to start thinking about how a line can intersect a plane. So I think this is a really good visual. Another visual, if you want to take a piece of paper and maybe like a pen, you might be able to see this a little bit easier. The piece of paper would obviously be your plane and the pen would represent the line. So our first option would be if we have a plane and a line that are parallel and do not intersect at all. Now in this case, there's no solutions. And we could say, sorry, it's getting very messy here. We could say that the line and the plane are parallel and distinct. Our second option would be if the plane and the line intersect at one point. So to visualize this, you could take your piece of paper and your pen and poke the pen through the paper at one point. So this would give us obviously just one solution. And the third option would be if the line was completely contained in the plane. So for this one, there's an infinite amount of solutions. So basically, any point that was on the line or satisfied that equation of the line would be a solution. So we're going to be going through this in the next section, but just for now, I thought it would be fun to think about how you think two planes could intersect each other. So if you have two pieces of paper, what kind of ways could those two pieces of paper intersect each other? I will give you the solutions to this in the next section. So in example 1, we're going to be determining how these two lines intersect. So our first observation, or the first thing that I want you to take a look at, is if these two lines are parallel. So if I take a look at these direction vectors, so our first one is 2, 1, negative 3, and our second one is 1, 5, 5. Those are not scalar multiples of each other, so we know that these two lines are not parallel. So the next thing that we're going to do, and you can see that I have them written here, I'm writing these equations in parametric form. So because these two lines are not parallel, we know that out of the 4 possibilities, we're down to 2. So we know that these two lines are either going to intersect at one point, or they're not going to intersect at all, and we're going to have some skew lines. So what we're going to do is we're going to come up with some equations. So we're going to set the x equal to the x, the y equal to the y, and the z equal to the z, and we're going to see if we can come up with a solution. If we do, that means we're going to have an intersection at one point, and if we can't, that means that we have skew. So when I set my x equation equal to my x equation, I'm left with my first equation, so 2s minus t equals negative 4. I did the exact same thing for y here, so s minus 5t is equal to 7. And then the same thing for z. So what you can see with this one is that after I set it up, I had a negative 3s minus 5t, and I just thought it would be nicer to work with positives, so I just switched sides for the left and the right hand side there. So 3s plus 5t equals negative 19 is my third equation. Now that I have all 3 of these equations, I am able to pick 2 of them to attempt to solve. And then what I'm going to do is once I get that solution, I'm going to plug it back into the third that I didn't use to see if it works. So there's substitution or elimination. You could choose whichever 2 equations you want. Oftentimes there is an easier way. So if you're going to use substitution, I would recommend using either equation 1 to solve for t or equation 2 to isolate s. What I'm going to do is I'm going to use elimination, and I typically don't love elimination as much, but I do notice that I have a negative 5t here and a positive 5t. So I'm going to go ahead and start that. So I've gone ahead and I've rewritten equation 2 and equation 3 on top of each other. Using my elimination, I know that I'm going to be left with 4s equals negative 12, which means that I'm going to divide both sides by 4, and I'm going to get s is equal to negative 3. Now I need to take that and I need to sub that into equation 2 or 3 again. So one of the 2 equations that I've already used, I'm going to, sorry, I should have wrote into there, I'm going to sub that back into equation number 2. So negative 3 minus 5t equals 7, negative 5t equals 10, and that means that t is equal to negative 2. So now that I have my s and my t, I am going to go back and I'm going to plug both of those back into the equation I haven't used. So I'm going to check in number 1. So when I look at the left side of this equation, I have 2s subtract t. So 2 times negative 3 subtract negative 2, which is negative 6 subtract negative 2, which is like negative 6 plus 2, which is negative 4. And if I look at the right side, it equals negative 4. So I do have a left side equals right side situation. So I have run out of room and I am going to go to the next slide, but I need to take one of these parameters, it doesn't matter which one, and I need to plug that in now to figure out what my one unique solution is. So because these are all equal, I do know that I have one unique solution. So at this point we have two options. We could take our s equals -3 and sub that into line 1, or t equals -2 into line 2. I am going to plug my s into my line 1. So when I simplify this, I have 7 plus 3 times 2, which gives me 1. 2 plus 3 times 1, which is going to give me -1. Or -6 plus 3 times -3, which is going to give me 3. And then, of course, therefore, the system has a unique solution at the point 1, -1, 3. All right, so we're starting a new example here, and just like with the last example, the first thing that we want to do is take a look at our direction vectors. And what I notice with these two direction vectors is that they are just scalar multiples of each other. So this is being multiplied by -2. So this means that we have two options. Either these two lines are parallel and distinct, meaning they have no solutions, or they are the exact same, meaning that they would have an infinite amount of solutions. Checking which one of these two options is our answer is a lot easier than our last example. So basically what we're going to do is we're going to take a point on line 1 and we're going to see if it is also a point on line 2. If that's the case, then we know that these two lines are the exact same, that they're coincident. So in order to check if the point from line 1 was on line 2, I've created parametric equations for my line 2. And what I'm going to do is I'm going to plug in this point into these equations to see if I get the exact same value of s for all three. If I do, then I know that these two lines are coincident and we have an infinite amount of solutions. If I don't, then these two lines are parallel but distinct. So I've set these three equations up, and I'm going to go ahead and I'm just going to start solving them here. So I'll start with the bottom just because it's the easiest. I'm going to get s is equal to 2/3. And in this one, I'm going to bring my 5 over. It's going to become a -8 divided by -4. I'm going to get s is equal to 2. And then in this top one, I bring my -1 over, and I'm going to get s is equal to 3 over -2. So because these s's are not all the exact same, I know that these two lines are parallel and distinct. So this means that there's no solutions. So in this last example, we're going to be seeing if this line intersects the plane, and if it does, how. So the first thing that I want you to notice is that our L1 is written the same as normal, but our plane is using notation pi, so oftentimes we'll use that if we're describing a plane. So the first thing that I'm going to do, you can see that I just took the information in line 1 and I rewrote it in parametric equations here. So I'll just show you how I did this first one. So my x is equal to 2 plus 3s, y is equal to -5 plus 2s, and z is equal to 3 plus 1s. Now what I can do is I can take this information and in my equation of a plane, wherever I see an x, I can plug in the information from my parametric equation. Same thing with my y and my z. So I've just written this out for you. Again, all I did was I plugged in the x, the y, and the z from my parametric equations. And I'm going to go ahead and I'm going to solve this. And if I can solve for s, that means I am able to get a point of intersection. So what you can see that I've done here is I've just expanded this out in this first line. And then combined like terms, and I was able to solve for s. So I was able to say that s is equal to -5 over 2. What I'm going to do now is I'm going to take that and I'm going to plug it back into the equation of a line. So as you can see, I've just plugged my s in here and solved. So 2 minus 5 over 2 times 3, I get negative 11 halves. Same thing for my y and my z, so negative 5 minus 5 halves times 2 gives me negative 10, and then 3 minus 5 halves times 1 gives me 1 half. So what I found here is that this point is the point of intersection between the line and the plane.